In this section, we'll talk about the speed of waves, the speed of light waves, and the speed of sound waves. So to get started, let's talk about the speed of light, the speed of sound. We have light waves, which are transverse waves. They're generally drawn like this. We have sound waves, which are a type of longitudinal wave. They're generally drawn like this: compression, rarefaction, compression, rarefaction. Or they might be drawn like a slinky that has compressions and rarefactions. Compressions, rarefactions. Compressions, rarefactions. All right, so basically close together, far apart. Okay, so that's what a sound wave is drawn like. Now, in a very general sense, there are going to be lots and lots of exceptions to this very general statement. But in a very general sense, light waves are going to travel the fastest through a vacuum. They will travel a little bit slower through a gas, such as the atmosphere. They will travel a little bit slower through a liquid, such as water or corn oil. And they'll travel the slowest through a solid. Again, this is a very general statement. There will be exceptions to this general statement. Light will travel fastest in a vacuum and slowest through a solid. In a very general way, sound waves are the complete opposite. Sound waves will travel fastest through a solid, a little bit slower through a liquid, slower still through a gas, and sound waves cannot travel at all in a vacuum. A vacuum is a place where there are no molecules, such as outer space. Or if you take a jar, a sealed jar, and you pump out all of the air, pump all the little molecules out, there will be no sound. So again, sound requires a medium to travel through. Sound cannot travel through the vacuum of space. Sound will travel fastest in a solid and slowest in a gas. So in a very general way, light and sound waves, the speed of light and sound waves is basically opposite each other in the different types of phases of matter. Right? And again, vacuum is the absence of matter. There are no molecules, and only light can travel in outer space. Sound cannot travel in outer space. What that means also is that if I could stand on the moon and a friend could stand a few feet away from me, what would my friend hear when I was talking? My friend wouldn't hear anything at all because there's a vacuum up on the moon, very, very little atmosphere, almost no atmosphere. And so the sound waves couldn't travel 2 inches, let alone the few feet between my friend and I. All right, so we understand a little bit about the relative speed of light and sound in different media and different phases of matter. Now, what I'd like you to do is go to the front of your reference tables, go to the front page, and copy down the speed of light in a vacuum and the speed of sound in air. All right, so the speed of light, which is a specific symbol c. So c is a type of v velocity. And for light, that would be 3 times 10 to the 8th meters per second. You shift that over just a little bit. All right, so the speed of light c is a velocity. You can plug it in for v into an equation. Is 3 times 10 to the 8th meters per second. Now, the speed of sound in air is 3. Now, this says 3.31. I'm just going to round that down to 3 times 10 to the second meters per second. Because what we want to do first is look at the relative magnitude of the speed of light compared to the speed of sound. How many times greater is the speed of light as compared to the speed of sound? All right, so if you take the speed of sound, 3 times 10 to the second meters per second, how many times would I have to multiply that by to get to the speed of light? 3 times 10 to the 8th meters per second. So I'm going to take 3 times 10 to the 8th, divide it by 3 times 10 to the second. In other words, comparing the two of them, 3 times 10 to the 8th divided by 3 times 10 to the second. All right, and I'm getting 1, 2, 3, 4, 5, 6. All right, I'm getting 10 to the 6th. So light is 10 to the 6th times faster than sound. Light is much, much faster than sound. Let me show you another way that you can write this. All right, 10 to the 6th is the number 1 million. Light is 1 million times faster than sound. Because 1 million is 10 to the, here's the decimal point, 10 to the 1, 2, 3, 4, 5, 6. All right, so light is 1 million times faster than sound. All right, if you compare the speed of light, 3 times 10 to the 8th, to the speed of sound, I'm rounding it to 3 times 10 to the second. All right, you're going to get 1 million times faster. All right, so light is much, much faster than sound. And this manifests itself when you see lightning, you hear the thunder afterwards. So the lightning and the thunder occur at approximately the same time, but you see the lightning first and you hear the thunder later, because the light gets to your eyes before the thunder gets to your ears. All right, so light is faster than sound. Now, I'd like to mention one other kind of neat little explanation of the fact that light is faster than sound. When you have a radio station, right, here's the radio station, and the radio station has an antenna, and they send out waves. Well, what kind of waves are they sending out? Here's the radio station with their antenna. I'll call this a radio station. And here's your table, your picnic table in the backyard. And on top of your picnic table is your radio. Your radio also has an antenna. And you know that out of your radio comes sound waves, right? You hear the sound waves. And here's your ear, all right? So you hear the sound waves that come out of your radio, or your iPod for that matter. I'm sorry, no, an iPod wouldn't have an electronic transmission. Never mind about that. Here's your radio, all right? So here are the sound waves coming out of the radio. Compression, rarefaction. Compression, rarefaction. The sound waves are going from the radio to your ear. Now the question is, what kind of waves does the radio station use to transmit the music or the talk from the radio station to your radio? Well, your radio is pretty far away, but you hear the sound almost as quickly as the radio station is putting it out into the air. And why is that? Because the radio waves are light waves. They're very, very fast. So the radio station emits light waves. So I'm going to draw the light waves, the radio waves, as a transverse wave, all right, coming from the radio station to your radio. All right, so the radio station has the antenna the radio station transmits radio waves, and radio waves are a form of light waves. They're very, very fast. They get from the radio station, which might be 50 miles away or 100 miles away or even further than that, and transmits those radio waves to the antenna of your radio, and the radio changes those radio waves into sound waves that you can hear. And since you're very close to your radio, it's okay if the sound waves are slow because they don't have to travel very far. All right? So again, a nice illustration of the difference between light waves, which are very, very fast, transverse waves, and sound waves, which are much, much, much slower, and longitudinal waves, is the concept of how the radio broadcast is transmitted from the radio station to your radio. Right? Since the radio station is very far away, it would take minutes, hours, days perhaps, for the sound waves to get from the radio station to your radio. That would be way too long, especially for a news program. So you use light waves to transmit the radio broadcast. Light waves are much, much faster, and they get quickly from the radio station to your radio so that you can hear the radio broadcast almost as instantaneously as it's being produced at the radio station. All right, so radio waves are light waves. All right, and the radio turns those light waves into sound waves that you can hear. All right, so we've got that. All right, now let's do some simple calculations with the speed of light and the speed of sound. All right, here's our basic equation. V equals F lambda. And keep in mind that for light waves, we'll do light waves first. For light waves, the speed will often be c. All right, they'll use c when the light is traveling in a vacuum or when light is traveling through air. All right, because when light is traveling through air, it's just a little bit slower than when it's traveling through a vacuum. Technically, c is the speed of light in a vacuum, but we will also use that speed when the light is traveling through air. All right. Now, let's say that the frequency of the light that we're dealing with is 4.5 times 10 to the 14th hertz. All right, that's 1 over seconds. All right, and we want to know the wavelength of that light. Now, this light is traveling through a vacuum or through air, so that means that the speed, or c, from the front of the reference tables is 3 times 10 to the 8th meters per second. All right, so let's solve for wavelength. We have frequency and velocity. They're asking us for the wavelength. All right, and let's get wavelength by itself. So wavelength is going to be V over F. All right, we'll recopy that. Wavelength is the velocity over the frequency, and the velocity is c. All right, so the velocity is 3 times 10 to the 8th meters per second. And the frequency of the light is 4.50 times 10 to the 14th inverse seconds. All right, let's divide. All right, 3 second E 8 divided by 4.5 second E 14. Or negative 14? 14, okay. All right, so the wavelength that we're getting is 6.67 times 10 to the negative 7. And the unit is going to be meters. Let's see how this works out to meters. All right, seconds over 1. You invert, multiply bottom and top, seconds over 1. The seconds cancel, these seconds cancel, the unit you're left with is meters. All right, so the wavelength of this light is 6.67 times 10 to the negative 7 meters. All right. Now let's try another problem where we're given the frequency and the wavelength and we calculate the speed of the light. All right. So again, in this problem, we were given the frequency and the speed we looked up on the front of the reference tables. We were given the frequency. Matter of fact, if they gave us just the frequency, we would look up the speed, we calculated the wavelength. All right? Now, what if they give us the frequency and the wavelength and ask us to calculate the speed of the light? All right? So let's say that the frequency is 6.2 times 10 to the 15th. All right, and for the wavelength, let's use 4.03 times 10 to the negative 8, all right, meters. All right, so let's try that and see what we get for the speed of the light. We'll figure out whether the light is traveling in a vacuum or not. All right, so we're going to take, they're asking us to find the speed of the light. Now, if we get 3 times 10 to the 8th, and we know that the light is traveling through either a vacuum or air. If it's slower, then maybe it's traveling through a liquid or some other gas, a liquid or a solid. All right. So let's calculate the speed. Speed equals frequency times wavelength. All right, here we go. The frequency, 6.20 times 10 to the 5th seconds. Multiply 0.03 times 10 to the negative 8 meters. Let's multiply these two together and see what we get. 6.2 second E 15 times 4.03 second E negative 8. All right, when I multiply these two together, I get I'm going to round up a little bit. I'm getting 2.498, so I'm going to round up to 2.50 times 10 to the 8th. Let me just count these. 1, 2, 3, 4, 5, 6, 7, 8. Very nice. And this is meters over 1 times 1 over second. See the unit? Meters is really meters over 1 times 1 over second. So this is meters on top, seconds on the bottom. Meters per second is the unit. So you can see very clearly that this light is not traveling through a vacuum, and it's probably not traveling through a gas unless it's a very dense gas. This light is probably traveling through a liquid or a solid. That's why the speed is slower. Instead of 3 times 10 to the 8th, it's only 2.5 times 10 to the 8th. All right? But my main point here is that when you take the frequency of a wave, multiply it by its wavelength, you're going to get speed. Frequency is 1 over seconds. Wavelength is meters per second. Meters. All right, 1 over second times meters is going to give you meters per second for a unit. So multiplying frequency times wavelength gives you speed. All right, and the units. Look at the way the units work out. This is one way to remember this equation. All right, 1 over seconds times meters over 1 is going to give you meters per second. Okay? Now, that's light waves. All right, let's take a look now at a sound wave. All right, if we take a sound wave at standard temperature, that would be 0 degrees Celsius. So they'll give us the frequency of the sound wave, and they'll give us the wavelength of the sound wave. Now, for the wavelength of the sound wave, for the frequency of the sound wave, let's take something like 10,000 hertz. All right. For the wavelength of the sound wave, let's take something like 3.31 times 10 to the negative 2, excuse me. And we're going to calculate the speed of this sound wave. All right, so the speed is going to be the frequency times the wavelength. Okay, take the frequency, 10,000 hertz, multiply that by the wavelength, 3.31 times 10 to the negative 2 meters. All right, multiply those two together. All right, 3.31 second e negative 2 times 10,000, and we're getting 331 meters per second for the speed of this sound wave. Now, let's try the same sound wave, but at a higher temperature. The same sound wave at a higher temperature. So we'll keep the frequency the same, 10,000, but we'll raise the temperature and see what happens when we raise the temperature of the sound wave. What's going to happen here? Okay, so the wavelength is 3.4 times 10 to the negative 2 meters. So what's the speed of sound at this higher temperature? All right, speed is frequency times wavelength. So let's take 10,000 for the frequency, multiply that by a wavelength of 3.4 times 10 to the negative 2 meters. All right, 3.4 times 10 to the negative 2 times 10,000 equals 340 meters per second. All right, so what have we found here? All right, at the higher temperature, the sound waves travel faster. Okay? Now, it's the New York State Regents Physics syllabus wants us to know that sound waves travel faster at a higher temperature. But it stops right there. We're not going to be asked to do any calculations involving temperature. We are asked to do calculations involving frequency times wavelength. All right, but it's nice to know that sound waves travel faster at a higher temperature. All right. So again, just to summarize what we've talked about here in terms of speed. All right, before I summarize, let's just do one more. Let's do a graph also. Okay. This might be some other kind of a wave, maybe a water wave, just a wave going up and down in the water. All right. Let's calculate the speed of this wave. All right. So we're going to need to know the distance. We'll do that in meters, and the time. We'll do that in seconds. All right, so let's say the distance here, I'm making up any old little problem here. Let's say that this is 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. Down here, we'll put 1 second, all right? 1, 2, 3, 4, 1, 2, 3, 4, 2 seconds. Okay? And we're going to calculate the speed of a wave. Now, since I've already set a certain distance in a certain amount of time, every wave that I put on this graph will have the same speed. And this graph will just be for transverse waves. But, so, basically, no matter what wave I put up here, the speed is going to be the same. And this illustrates the concept that the speed of a wave depends upon the medium that it's traveling through. This graph basically represents a medium. The speed of any wave that you put on this graph is already set because you've said that a certain distance is covered in a certain amount of time. So let's calculate what the speed of this wave would be. If the wave, now the equation for speed, distance over time. So if this wave covers 4 meters in 2 seconds, all right, 4 meters were covered in 2 seconds, that means that the speed of this wave, any wave we put on this graph, is going to be 4 meters per second. All right, so it doesn't matter if I put this wave, all right, or a wave with a much higher frequency, much shorter wavelength. Here's a high frequency wave with a much shorter wavelength. I'm going to do the same amplitude. All right? I'm going to make a wave now with a much higher frequency, much shorter wavelength, but the same amplitude. Here we go. Da-da, da-da. Okay? So this is higher frequency. It's many more cycles in the same amount of time, a much shorter wavelength, but the same amplitude as the original wave. Yet, the speed of this wave is the same as the speed of that wave because they're on the same graph together. So let's calculate the speed of this wave right now. This wave covered 1 meter, see that 1 meter there, in a half a second. If that's 1 second, that's a half a second. So how fast is this wave going? The speed is the distance divided by the time. The distance divided by the time, all right, is 1 meter in a half a second. Take your calculator. 1 divided by 0.5 is going to be, again, 2 meters per second. So you see that the way it works out is that when you have a graph and the distance and the time are set, or even if they just tell you the distance, and then they tell you in the text that the time from, for example, A to B is a certain amount of time. It's the same thing as if we set the time on the axis, that the velocity of any wave that you put on this graph is now going to be the same. The wavelength can vary, the frequency can vary, the amplitude can vary, but the speed of these two waves is the same. All right. Now, just a little bit of a summary here. One of the things that we've talked about in terms of speed is that the speed of light, well, the speed of any wave, the speed of light depends upon the field or the medium that it's traveling through. The speed of sound depends upon the medium, the material that it's traveling through. When you put a wave on a graphical picture, on a graph, the speed of that wave depends upon how you set up the graph that you're putting the wave on. All right? So the speed of light is going to be fastest in a vacuum, slowest in a solid. The speed of sound is going to be fastest in a solid, slowest in a gas. Sound cannot travel in a vacuum at all. So again, the speed of the wave depends upon the medium that it is traveling through. Or in the case of light, the field that it's traveling through. Because when you're traveling through a vacuum, the light is traveling based upon a field, not a medium. The speed of light is in general faster than the speed of sound. When you look at the speed of light in air and the speed of sound in air, the speed of light in air is 3 times 10 to the 8th meters per second. That's c. All right, the speed of sound, I'll just put v sound, is much slower, 3 times 10 to the 2nd meters per second. All right? And again, a neat little way to remember this is that radio waves, which are a form of light, get to us very fast from the radio station because they are a form of light. Once they're if we want to hear them, they have to be converted into sound, and the radio is going to have to be fairly close to us so that we can hear the radio broadcast quickly when those very slow sound waves are traveling to our ears.